Okay, so this lecture we will now come down to some of the stereological relationships that you have seen, but how do we get them, how do we derive them, that you would be seeing, and some of them that you have seen. Volume fraction, of course, you have seen there is nothing much to derive. I think it has been derived in some sense, but I will still show you a more rigorous derivation of how volume fraction is related to area fraction. Then you have surface area per unit volume. How do we get at that? Length per unit volume, if I have linear elements in a microstructure like dislocations, and if I have precipitates, so I want to count the number of precipitates per unit volume, so numerical density. So these are the four relationships we will first see. And if you look at this slide actually introduces some of the stuff that you have seen, and it kind of introduces a kind of symbols that one uses in stereology. So on your left are those four fundamental parameters that we want to measure. Volume fraction, we use the symbol V sub V, surface area per unit volume S sub V, length per unit volume L sub V, number per unit volume N sub V. On the right hand column are the measurements that one can make on a two dimensional microstructure. So point fraction is one that you are already aware of. Length fraction I will be introducing what it is. Area fraction by now you are aware of. PL, number of intersections per unit length, that also you are aware of with a grid of lines. Number per unit area. So if you are having particles, how many particles that you see on a two dimensional image. In points per unit area, how do we get points on a microstructure? Well, if you have linear elements in 3 dimensions, you would get points on a two dimensional image. So the right hand are the measurements that you can make, and these measurements are then related to the left hand side are the parameters of the structure that we want to estimate. So you will see that all of these measurements, whether on the left hand side the parameters or the measurements on the right hand side on the two dimensional image, are actually ratios of two quantities, okay, x by x upon y. So for example, if I look at area fraction, it is area upon area. If I look at number per unit area, it is number upon area. If on the left hand side I will look at surface area per unit volume, so x is area and the denominator is volume. And in general, this is the way we have defined the symbols as well, x subscript y, to keep things simple. And we will now explore the relationships between the measurements made and the parameters to estimate. So let us begin with volume fraction. Considering volume fraction, you already know that if I measure a point fraction on a microstructure and make number of measurements, get an average value of point fraction, then this becomes an estimate of the volume fraction. Now another way of relating volume fraction, so this is like one. Another way we can relate volume fraction is through area fraction. So I make measurements of area fraction on several images, get an average value of that, and this becomes also an estimate of volume fraction. Now this is what I am going to now show, that this relationship we have already shown is true. Now we will look at this relationship and show that this is also true directly without going through the point fraction. So, in all these cases what I am going to take is a three dimensional space, a cubic space, the way I have taken for many other situations. I will simply take basically you can imagine it is a block of material, okay, in the shape of a cube whose dimensions are L. In this I have these second phase particles distributed inside the three dimensional structure, and I take a section through it I will take the horizontal. So, let me also label the axes, so that this is my x direction, y direction and z direction. If I look at this microstructure, I will see particles which are sectioned by this plane probe. Let the area fraction observed on this be A sub A, and it has been sliced at some random distance z. Okay. So, that is why this is being referred to as area fraction at position z. Now, imagine if I section this at different positions of z, what I will get if I were to plot all the way from 0 to L, z varying from 0 to L, area fraction z, obviously at different sides I am going to get somewhat different values of area fraction, and it may vary in some seemingly erratic manner. Okay. Somewhere it will be higher, somewhere it will be lower, and there will be some kind of an average. If I were to add up all of these, then I will get an average area fraction. So, let us look at it this way. If I have to now find an average area fraction, what I can do? I can integrate this function. I can integrate this function from 0 to L Az dz, and here I have to divide this integral by L to get an average value. This is of course assuming that my all positions of z are equally likely, then only this average function works. Let us do a little bit of manipulation here. Suppose I multiply and divide by L square, that is area of a single section. If I do this, this will become 1 upon L cube integral 0 to L area fraction at position z times L square, which I am keeping inside the integral. So, all I have done is I have multiplied and divided by L square. Now, what is this quantity? AAZ times L square, this is nothing but the total area of these particles observed at position z. So, this could be then written as AZ, right. This is the area fraction, then if this area fraction is multiplied by the total area, then that gives you the total area of the particles. So, this becomes 1 upon L cube integral 0 to L Az dz. Now, this integral Az dz. So, if I look at just quantity Az dz, this is the volume of the particles in a thin infinitesimal slice. Of thickness dz. And what is happening in this integral? I am adding all of these thin slices, infinitesimal slices all the way from 0 to L. What would that give me? This integral, that will give me the total volume of the particles, right. So, this would be the total volume of the particles divided by the volume of my cubic space. Now, this is nothing but volume fraction. So, this formally shows that this relationship is indeed correct, that the area fraction is an estimate of volume fraction. A third possibility is I take a microstructure in which I am seeing these particles, if I superimpose on it a line or a grid of lines, it does not matter, and I measure these intercept lengths. So, this could be L1, out here the length intercepted between a particle, this could be L2 and this could be Li and so on. All the particles that the line goes through, you measure the length intersected within the particle. Okay. If I sum all of these lengths which are intersected within the particles divided by, and you divide the sum by the total length of the line or lines. Okay. I can put a set of parallel lines and do this exercise. So, divide this by L, that this is called, just like you call area fraction, this we can call it as the lineal fraction or length fraction, I should say, you can just call it length fraction, that the fraction of the length of this line intercepted between the particles from one boundary to another boundary. This is also an estimate of volume fraction. Now, I am not going to prove this, but it is easy to prove. You can prove it the way this has been proved. On a two-dimensional section, you can prove that length fraction is actually area fraction, and since we have already proved that area fraction is volume fraction, the relationship volume fraction is estimated by the length fraction becomes true. So, essentially I have put down three different ways in which we can measure volume fraction. This relationship is generally not used for estimating volume fraction in materials. So, we will ignore this, and I want to look at these two methods of measuring volume fraction, and I want to analyze, I am going to analyze it very briefly. I am going to show you a kind of a statistical analysis, but in a very brief manner, that what would be the relative errors involved in estimating volume fraction by doing point count, by doing aerial analysis, and then try to see which is a better method of estimating volume fraction. So, let us look at first aerial analysis, I am going to skip most of the steps in this statistical analysis because that is quite involved. But let us do the following, that I have a microstructure which consists of second phase particles let us say that, suppose we say that all these particles are of the same area. Okay. So, let us say all, to begin with, if I assume that all particles are of same area A, and there are m such particles. Okay. And the total area of my field of view or my microstructure is A, capital A. Then clearly the area fraction would be total area of the particles divided by the area of my region over which I am measuring the area of the particles. So, the total area of the particles is simply m times A, and the field over which I have made the measurement is capital A. So, my area fraction is simply m small a upon capital A. But of course, now imagine that m here is a random variable. I will get some number of particles in one field of view, I will get another number in another field of view and so on. And we had shown earlier in one of the lectures that m can be modeled as following a Poisson's distribution. Okay. So, m follows a Poisson's distribution which is actually x to power mu upon x factorial e to power minus mu. This was the probability density function for the, or rather not, there is a probability function for the Poisson's distribution, which is a discrete distribution where x takes up integer values. So, x here is the same as m here. Okay. So, I want to find out what is the variance or the standard deviation sigma in my area fraction measurement. Well, I do know from the property of the Poisson distribution that the variance sigma square is equal to the mean value mu. Now, suppose on an average my mean value of m is m bar, okay, then the variance of m would be equal to the mean value, which is m bar. Okay. Now, coming back to this, what would be the variance then in area fraction? The variance in the area fraction is going to be, and we use a property that if x is a random variable and if it is multiplied by some coefficient c, then this gives me another random variable y, and if variance of x is sigma square x, then variance of y is equal to c square sigma square x. Okay. This comes from this comes from what is known as propagation of variance from one random variable to another random variable, and this is a linear relationship. So, this holds. So, here what would happen, C is my small a upon capital A. So, my variance in this is sigma square m times a upon a and squared. Now, but I know that variance of m is nothing but the mean value of m, because it is following a Poisson's distribution. So, this becomes m bar times small a upon capital A squared. Then I can write that the variance in the measurement of area fraction or the estimation of area fraction, I can let me divide this by the average value of the area fraction squared. This is nothing but variance in the volume fraction estimation divided by the average or the mean value of the volume fraction squared, and this is simply equal to m bar a upon a squared divided by what is the average area fraction? It would be m bar into small a upon capital A. M bar small a upon a, and this whole thing has been squared. So, I need to square this. So, what I will get from here? What I will get from here is small a upon capital A will get cancelled, and this will be m bar and below would be m bar square. So, this will become 1 upon m bar. Now, this sigma v upon v bar, this represents kind of what I can call it as relative error in my measurement. Okay? Because sigma volume fraction is nothing but the standard deviation. So, the dispersion in the volume fraction estimate divided by the mean value of the volume fraction. Okay. So, this is it is relative to the mean value. You have normalized it with respect to the mean, and so this represents on the left hand side then square of the relative error. Okay. And I will call this relative error as RE subsequently. Now, in this simple derivation, the error is simply related to, the relative error is simply related to how many particles you actually measure, their areas. Okay. To whether you are going to measure 100 particles, 200 particles, 500 particles, now is going to depend on what kind of relative error you can take, right. Can you take 10% error, or you can take 5% error? But this is only a approximate result I have produced here. In the sense, what I started with, I assumed that all of these particles had the same area A, but we know that is not going to be true. There is going to be an average area of the particles, and there is going to be some kind of a standard deviation that would be there. So, there will be there is going to be a distribution of areas that, so therefore, the standard deviation in the areas themselves should also contribute to my error, and that rest of the analysis I am going to skip how I can get it, but it can be shown that this is equal to 1 upon m bar times 1 plus sigma a upon a bar squared and the whole bracket closed. So, this is 1. For constant size particles, sigma A would be 0. So, I come back to the same relation, but then there is an added relative error that has been added because of the distribution of areas of particles. So, this is an important relationship which we will see soon, how how many particles I should measure in order to keep my relative error within desired limits. Now, the same analysis you can do with point count. Okay. If I use a point count technique for estimating volume fraction, and I am going to skip in fact all the steps of the derivation, because that is even longer, because there you will get Poisson's distribution would have to be taken into account, and you will also have to consider what is the probability of a point falling inside the particle which is going to follow a binomial distribution. Two together put together gives me a very interesting result. If I have a microstructure of isolated particles again, in which I put a point grid with the restriction that the grid size is larger than the longest dimension of the particle. Okay. So, the grid size is greater than the longest particle dimension, then all it means is that only one point can fall inside one particle. That is what, by putting this restriction, only one point falls inside the particle, we can show that the relative error squared in the estimate, where the estimate is given by the point fraction, which is equal to small n upon capital N, where small n is the number of points falling inside the particle, capital N is the total number of points in the grid. This is simply equal to 1 upon small n. Okay. Now, let us compare these two results and then decide which is the method I should use for estimating volume fraction. In order to do this, let us consider a structure which has same size spherical particles. Okay, in the 3-dimensional structure, I have the same size spherical particle. So, what I am going to see on the 2-dimensional structure, am I going to see same size circular particles? No, I am going to see variable size circular particles, depending on where the section cuts the spherical particles. So, this would have an A bar and a standard deviation of the area of the particles. It can be shown that if my spherical particles are of the same size, then sigma A upon A bar squared is approximately 0.2. Again, we are not going to prove this, okay, but this can be proved again from geometrical probability of cutting the particles. So, I know for this, if there was a distribution of the sizes in the spherical particles, then this variation is going to be even larger. So, this is the minimum possible variation you would get in the 2-dimensional microstructure. Hence, the relative error can be written as can be approximately written as 1.1 upon square root of m, where m is the number of particles measured. Okay, so I have removed the square part so that I get directly relative error by measuring the areas. Okay, if I am doing an areal analysis, then this is going to be my relative error for constant size spherical particles. So, suppose I want, let us say, how many particles do you think I need to measure if I want to restrict my relative error to 10%? 10% means 0.1 here. Okay. So, what do you think? M would be of the order of 1.1 upon 0.1, well, m would be equal to squared, and this would be approximately 120. So, I should measure areas of at least 120 particles just to restrict my relative error to 10%. If I want to restrict it to 5%, I need to measure 1.1 upon 0.05 this time squared, and this would be of the order of 500 particles I need to measure. And let us say I want to be very accurate, keep it to 2% error, where I do not want more than 2% relative error. Then m would be 1.1 upon 0.02 squared, and this you would get a greater than 3000. I need to measure 3000 particles. Okay. So, I need to measure areas of 3000 particles to keep my relative error within 2%. If I want to keep it within 5%, I need to measure at least 500 particles. On the other hand, by point count, I am going to be very similar, because this is going to be here for point count. For point count, the relative error is going to be 1 upon square root of n, which is very similar to 1.1 upon square root of m. So, I am going to get very similar result, that if I have to keep my relative error within 5%, I need to measure 500 areas of 500 particles. By point count also, if I want to restrict my error within 5%, I need to do count of or at least 500 points must fall inside the particles, and I would simply have to count. Which do you think would be a easier method to get the same relative error? If I told you that you take and start measuring the areas of each particle, get me area fraction, and that gives me estimate of volume fraction, and or use another method like point count and just count the number of particles to keep my relative error within 5%, which method is going to be, which method do you think would be easier to do? Because in one case you have to do purely point count, no area measurement is involved of individual particles. Here I will have to measure areas of 500 particles. In which case I will be covering a larger area of my sample, point count, because to get 500 points inside the particles, I will have to cover a much larger area than this. that may be all right, because our samples are if my sample has large enough area, I can easily cover that and do counting much faster, more efficiently, with less chances of error versus measuring area. So, whenever I have to measure volume fraction manually, if that point count technique becomes the superior technique for estimating volume fraction. When I can use a grid which is very coarse, so very quickly I can count and cover a large number, a large area in the sample. So, point count becomes more efficient. But if I have a microstructure which is such that automated image analysis can perform this analysis, then perhaps even area fraction might be a better way to go, if automated image analysis is possible. If it is not, then almost always point count is going to be the superior technique or the more efficient technique. So, generally you should adopt a strategy for measuring volume fraction. So, if I am, one is you can take digital images, this is my sample. So, I should move the sample under the microscope in a systematic manner. So, I can take one view here, second here, third here, fourth here, and so on, and then move down. So, this is the way. If we do this systematically, instead of just here and there, like that, do a systematic scan of the sample and take images like this, and then put your grid on these images to estimate the volume fraction, because you need to take large number of areas if you want accurate results. Okay. So, this is important point to consider, and this would be an important point to consider for all other measurements as well. Okay. Are there any questions I can answer to this? Okay. So, this completes my volume fraction estimation. Let us look at now those other estimates, and we need to show them how those stereological relationships get derived.